Let's do electron configurations for the second period. So we find the second period on the periodic table, and we go across, and the first element we see is lithium with 3 electrons. So 3 electrons to worry about for lithium. Let's think about the first 2 electrons for lithium. The first 2 electrons for lithium are going to go into the first shell. So we talked about this in the last video. The first shell, when n is equal to 1, right, the only possible value for L is 0. So we're talking about an s orbital. And there's only one s orbital in the first shell here. So I can draw in, let me go ahead and draw that orbital in. So here's the 1s orbital in the first shell. So lithium has 3 electrons. The first 2 electrons for lithium are going to go into this 1s orbital. So we pair up our spins like that. So writing the electron configuration for lithium, let me go ahead and we'll start writing it right here. So we have 1s2 so far. Well, lithium has 3 electrons, but the first shell is full, right? It's closed. So we have to move on to the second shell to add in lithium's 3rd electron. So in the second shell, n is equal to 2. What are the allowed values for L? L could be equal to 0, or L could be equal to 1. So we talked about that again in the videos on quantum numbers. So when L is equal to 0, we're talking about an s orbital. So in the second shell, in the second energy level, we also have an s orbital, and we also have 1 of them. And we also have to think about L is equal to 1. That's talking about a p orbital. The allowed values for ML would be -1, 0, and +1. So 3 possible values, right, means 3 p orbitals here. So we have 3 p orbitals in the second energy level as well. So let's draw those in on our orbital diagram over here. So we already drew in this s orbital in the first shell, right? Next, let's draw in this s orbital in the second shell, the second energy level. It's of higher energy, right? So we draw it in here. So this is the 2s orbital, right? And then we also have p orbitals in the second energy level. We have 3 of them. So we draw in our p orbitals in the second energy level. They're of higher energy. So here are the 2 p orbitals, and there are 3 of them. So one of them would be 2px, one of them would be 2py, and one of them would be 2pz. It doesn't really matter which one is which. We'll just draw them in there like that so far. All right, so lithium, we've taken care of the two of its 3 electrons. Its 3rd electron has to go into this next highest orbital in terms of energy, right? So that would be the 2s orbitals. We have energy going up this way, right? So as you get higher and higher, energy increases. So lithium's next electron, right, as you build up the lithium atom, must go into this orbital here, right, the 2s orbital. So therefore, lithium's electron configuration is 1s2, 2s1, and remember what these numbers mean. So this means that there is 1 electron in an s orbital in the second energy level. So we have 1s2, 2s1 for lithium's electron configuration. Let's do the next element. So that's beryllium. Beryllium has 4 electrons to worry about. So for beryllium, if you look at the diagram, let's see if we can just make a different color here for beryllium. So let's make beryllium red here. So 1 more electron. So we can put beryllium's 4th electron into this orbital and pair up our spins. And so let's write the electron configuration for beryllium. So it'd be 1s2, and then we have 2 electrons in the 2s orbital. So we'd write 2s2 here like that. All right, now we filled the 2s orbital. Remember, each orbital can hold a maximum of 2 electrons. We filled the 2s orbital. So when we move on to the next element, right, which is boron over here. So boron has 5 electrons. So let's write the electron configuration for boron. Well, so far we have 1s2, 2s2. But that only takes care of 4 electrons. We need 5. So where does the 5th one go? The 5th one goes into the next available orbital here. So we're going to put the electron in. The 5th electron for boron goes into a 2p orbital. So we would write 2p1, indicating that the 5th electron for boron went into a p orbital in the second energy level. So 1s2, 2s2, 2p1 is the full electron configuration for boron. All right, let's do carbon. So next we have carbon. Let's use blue for carbon here. So carbon has a total of 6 electrons. So we have 1 more to think about. So we know it's going to go into a p orbital in the second energy level. The question is, which one of these p orbitals do we put this next electron for carbon? So we have to think about something called Hund's rule, and so I'm never going to pronounce the German properly. So, but Hund's rule tells us that our goal is to minimize electron repulsion here. So let's think about, let me just go ahead and draw the p orbitals down here. So we already have one electron right here. Right? Well, it doesn't make any sense. It doesn't make any sense to put an electron into the same orbital here, right? Because that puts the electrons really close together in space. So if you're thinking about a p orbital, remember a p orbital is shaped like a dumbbell. So I'm just saying we have a p orbital on this axis, let's say. So we already have, I'll just use blue here. So we already have one electron in there. Doesn't make any sense to add an electron to that exact same p orbital, right? That puts them really close together in space, and electrons repel. So that doesn't make any sense. So we need to take that electron out of there, right? That doesn't make any sense. We need to add an electron to another p orbital. So we'll take this electron out of there like that. So remember, there are other p orbitals, right, on these other axes here, right? So here's another p orbital, and then here's another p orbital. So we need to add an electron to another one of these, whichever one, doesn't really matter. Let's just say we're adding one here, right? So we're adding an electron to a different p orbital, whichever one it is, px, py, or pz. And it turns out that keeping the spins parallel helps to minimize the electron repulsion for pretty complicated reasons, and I think they might be still doing research on this. And so we put the electron in a different orbital, and we keep the spins parallel, which helps to lower energy for the atom here. And so that's where we're going to put carbon's 6th electron. We're going to put it into a different p orbital, and we're going to keep the spins parallel like that. So we can go ahead and write carbon's electron configuration. Just read off everything we have on our orbital notation here. So we have 1s2, we have 2s2, and we have 2p2 here. So 2 electrons in the p orbitals in the second energy level for carbon. All right, so next we have nitrogen. So let's use green here for nitrogen. So nitrogen has 7 electrons, so one more electron to think about. So let's put nitrogen right here. So we have so far 1s2, 2s2. Now let's think about nitrogen. So we need to add one more electron to our diagram. Once again, we're going to follow Hund's rule here. We're not going to add the electron to one of the already occupied orbitals, right? We're going to add this electron for nitrogen to an unoccupied orbital, and we're going to keep the spins parallel to keep everything lower in energy. And so we have 3 electrons for nitrogen in the 2p orbitals, and so we write 2p3. So we have 1, 2, 3. So we have 1s2, 2s2, 2p3 would be the full electron configuration for nitrogen. All right, let's move on to oxygen. So let's pick. Let's see here. What color should we pick for that? Let's use orange here for oxygen. So we have 8 total electrons. All right. So for oxygen, let's see. Let's put oxygen right here. So far we have 1s2, 2s2. So how many more electrons do we need for oxygen? Oxygen has a total of 8 electrons. We already represented 4, so we need to represent 4 more. Oxygen's 8th electron, now that all of our orbitals are occupied, we can start to pair our spins. So we put oxygen's 8th electron in there, so we can start to pair up our spins. So we have 4 electrons in the 2p orbitals for oxygen. So we write 2p4. So 1s2, 2s2, 2p4. Notice if you add these together, right, 2 and 4, then you get 8, which is the total number of electrons that we had to represent for the electron configuration for oxygen. All right, let's move on to fluorine. So let's use a different green here for fluorine. So let's say fluorine right here, 9 total electrons. All right, so once again we're pairing up our spins. So we add fluorine's 9th electron to there, and we can go ahead and write it right here. So for fluorine, we would write 1s2, 2s2, and notice we have 5 electrons now. So 2p5 would be for fluorine. And then finally, let's go ahead and do neon here. So neon has 10 electrons. Right, so we have one more electron to account for. We have one more space, right? The last electron for neon would go into a 2p orbital here. So for neon, we would write 1s2, 2s2, 2p6. Notice we have no more places to put electrons, right? In the first or the second energy levels, we are completely full. So the second shell is now full, and if you wanted to add another electron, you would have to open up a new shell. You would have to go to the third energy level. And so you notice a pattern here emerging on the periodic table, right? So we said that hydrogen's electron configuration over here was 1s1. All right, and then we went over here to helium, it's 1s2, and then we moved on to the second energy level. All right, so this was lithium here ended in 2s1, and beryllium ended in 2s2. And then we filled the s orbital and moved on to the p orbitals. And notice we have over here, right? So boron's last electron was 2p1, carbon's 2p2, nitrogen's 2p3. Oxygen's 2p4, fluorine's 2p5, and neon is 2p6. So notice we have these 6 boxes over here on the periodic table. Those represent our p orbitals. And then over here on the left, we have these 2 boxes, right, representing our s orbital. And so that's the idea. The s orbital, we have one of them, holds a maximum of 2 electrons. We have these 2 boxes on the periodic table. Right, over here on the right, we had these 6 boxes, right, which is the maximum number of electrons that we can put into the p orbitals, because we have 3 p orbitals and each one can hold 2. So noticing these patterns on the periodic table helps you when you're writing electron configurations. You can just sit down and look at the periodic table and write them out after you've had enough practice. So make sure to do all of these again and think about electron configurations, where you're putting your electrons, and think about how it relates to the structure of the periodic table.